Hello engineers, this is Zubair. In this video, we will see about the design of beam. Okay, the design of simply supported beam. Here is given data. The width of the beam is 250 mm, and depth of the beam is overall depth of the beam is 500 mm. Okay, and effective depth is 450 mm, and effective cover is 50 mm, and span of the beam 5 meter, and the working load acting on the beam, that is 40 kilonewton per meter. Okay, so here FCK will be M20 grade of concrete and Fe415 grade of steel. Okay, so here first of all we need to find the sulfate of the beam. Okay, we need to find the sulfate of the beam. The solution is sulfate of the beam, uh, width of the beam into depth of the beam into density. Okay, width and depth into density. This 3 point, if you calculated this, 3.125 is the what sulfate of the beam, and this 40 kilonewton per meter is the service load acting on the structure. Okay, the total load will be 43.125 kilonewton per meter. 43.125 kilonewton per meter. Okay, so we need to take the factored load. So we need to take the what? Factored load. The factored load will be 43.125 into 1.5. This is the partial safety factor from the IS 456. From IS 456, the total factored load will be 64.6 kilonewton per meter. Okay, so using this load, we need to find the moment, maximum bending moment. Okay, so we have a formula for simply supported beam, WL square by 8. WL square by 8. So W is the 64.6 and L is 5 meter, 5000 mm, 5 meter, and divide by 8. So if you calculated this, you will find the 202.14 kilonewton meter. This is the moment. This is what? Moment. And we'll find the shear also. WL by 2 for simply supported beam. WL by 2, 64.6 into 5 divided by 2. It will get 161.5 kilonewton. Okay, this is the maximum bending moment. This is the maximum shear force for span of 5 meter of beam. Okay, again, so we need to find the mu limit. Okay, mu limit. This is the moment. This is the moment acting on the beam. So what is the limit of the moment? So mu limit. So we have a formula, 0.138 into FCK into BD square. 0.138 is for Fe415. Okay, 0.138 into 20. This is the M20 grade of concrete. 250 into 450 effective depth. Okay, so mu limit is 139.72 kilonewton meter. Okay, since here mu is greater than mu limit, can you see here? Our mu is greater than mu limit. Mu is maximum bending moment is greater than mu limit. So we need to design this beam as a doubly reinforced beam. If mu is greater than mu limit, then we need to design this beam as a doubly reinforced beam. Okay, so in doubly reinforced beam, what we need to do, we will provide the reinforcement at both sides, as well as in compression zone as well as in tension zone. That is called doubly reinforced beam. Okay, so here mu minus mu limit, this is 62.42. It will use in next steps. Okay, so next step is we need to find stress in compression steel. Okay, we need to find what? Stress in compression steel, that is called Fs. Okay, so if you refer SP 16 page number 13 table number 4, Fs is equals to d dash by d. So here we have a effective depth of the beam, we have considered 50 mm. D dash by d will be Fs. if you calculate this, 0.11 will be answer. Okay, so we need to find FSC. We need to find what? FSC value using SP34, page number 13, table number 4. Okay, so we don't have value for 0.11. We have a value for 0.1 as well as 0.15. For 0.1, 353. For 0.15, 344. For FE, 4 and 5 still. Okay, so we need to interpolation. Okay, so if you calculate this, we'll get FSC, that 352.8 Newton per mm square. This is the stress in compression steel. 352.8 Newton per mm square is stress in compression steel. Okay, so now we need to find ASC, area of steel in compression zone. ASC is what? Area of steel in compression zone. MU minus MU limit. We have calculated this here. MU minus MU limit 62.42. Okay, so MU minus MU limit divided by FSC into D minus D dash. Okay, 62.42 into 10 raised to the 6. Okay, so 350 divided by 352.8 into 450 minus 50. This is the effective depth and this is the effective cover. So area of steel in compression zone will get 444 mm square. 444 mm square. So using this, you can provide two number of 16 die of bar and one number of 12 mm die of bar. One number of 12 mm die of bar at the compression zone, at the top of the beam. Okay, so again we need to find the bottom steel. We need to find what? Bottom steel, that is AST2. AST2 is equals to ASC into FSC divided by 0.87 FY. Okay, what is ASC? Here is the ASC, 444 into 352.8 divided by 0.87 into 4 and 5. So we will get 434 mm square. 434 mm square. One more AST we need to calculate, AST1, that is we have a formula 0.36 into FCK B XU limit divided by 0.87 FY. Okay, here XU limit is the 0.48 into D. D is the effective depth. Okay, so 0.36 into 20 into 250 into 0.48 into 450 divided by 0.87 into 4 and 5. You will get this AST2 1077 mm square. Okay, 1077 mm square. So we need to add these two what is area of steel, 434 plus 1077. Here total reinforcement in area of steel in tension zone, AST1 plus AST2 is equals to 1077 plus 434 will be 1511 mm square. Okay, 1511 mm square. So using this AST, you can provide 3 number of 25 mm die of bar at the tension zone. 3 number of 25 mm die of bar at the tension zone. At the compression zone, 2 number of what? 16 and 1 number of 12 mm die of bar you can provide. Okay, so here these are the longitudinal reinforcement. We have find the longitudinal reinforcement. Now we need to find shear reinforcement. We need to find what? Shear reinforcement. Tau V is equals to VU in by BD. We have a VU that we have already calculated above, 161.5 into 10 raised to power 3 divided by 250 into 450. Here we will get tau V value is 1.43 Newton per mm square. Okay, so we need to find the percentage of steel in beam. PT is equals to 100 AST divided by B into D. So percentage will be 1.3. So using this percentage and using this tau V value, we need to find the tau C. Okay, refer IS 456 table number 19 for design of shear strength of concrete. Okay, so we have a value for we don't have value for 1.3. We have a value for 1.25, for 0.67, 1.5 for 0.72 for M20 grade of concrete. We need to find the value for 1.3 here. Okay, so tau C, if you make a interpolation, tau C is equals to 0.67 plus 0.72 minus 0.67 divided by 1.5 minus 1.25 into 1.3 minus 1.25. Okay, so you will get the TOSI value 0.68 Newton per mm square. 0.68 Newton per mm square. Okay. Now here TOV is greater than TOSI. Our TOV is greater than TOSI. So we need to provide shear reinforcement. Here shear reinforcement are required. If TOV is greater than TOSI, shear reinforcement are required. Okay. So here VUS is equals to, we need to provide a shear reinforcement in the beam. VUS is equals to VU minus TOSI BD. TOSI BD. Okay. VU we have already 161.5 minus put this TOSI value and B into D into 10 raised to the power minus 3. Okay. So we'll get VUS, that is 85 kilonewton. 85 kilonewton. So we can use two-legged 8 mm die of stirrups. We can use over here two-legged 8 mm die of stirrups. Okay. So we have a formula for spacing. SV is equals to 0.87 Fi ASV into D divided by VUS. If you put the values in this formula, you will get the spacing. Okay. So we will get spacing 191.14 mm center to center. Okay. So SV is greater than 0.75 D. That is 337.5 mm. Okay. Here adopt a spacing 190 mm. Here you can use this value SV. Adopt a spacing 190 mm near the supports, because we have maximum shear force at the supports. We need to make a spacing 190 mm near the supports, gradually increasing to 300 mm. We can increase the spacing at the mid of the zone of the beam. At the mid zone of the beam, we can increase, because at mid zone of the beam we don't have that much of shear force, so we can increase the spacing of the stirrups. Okay. At the support we can provide 190 mm center to center. At mid we can provide up to 300 mm center to center. Okay. So now we can check for the deflection. We have L by D actual. L is the 5000 divided by D. We'll get 11.1. If you calculated this using IS 456 table, percentage of steel is 1.3. We'll get the value LD max is 20.46. Okay. Our LD actual is 11.1. Okay. So LD actual is less than LD maximum. So our beam is safe in deflection also. Hence deflection control is satisfied. Okay. So this is the cross section of the beam. This is the cross section of the beam. Here I have provided at the top 2 number of 16 and 1 number of 12. At the bottom 3 number of 25 and 25 die of bar. Again here at the support, stirrups, 2-legged stirrups 190 mm center to center. At mid 2-legged stirrups 300 mm center to center. Okay. So this is the manual calculation of the simply supported beam using this data. So this beam we'll see in Etabs. Using same values, using same data, we'll see this design of this beam in Etabs also. We can compare the results. Okay, manual as well as in Etabs results. Okay. So now I will open the Etabs software. Here I'll take a new model. Okay. Here only we need only one grid. Okay, 2 grids, because we have 2 grids. This grid 1, grid 2. Here we need to provide what beam. So 5 meter of grid. Okay. So here I'll choose all the initial settings, codes and all according to the Indian standard and metric SI. Just click on OK. Here I'll take X direction. Number of grid lines in X direction we have 2, 1 and 2. Okay. Number of grid lines in Y direction, we don't have any grid in Y direction. I will just take 2. Okay. Spacing is 5 meter. Only one beam we are modeling over here. Spacing is 5 meter. In X direction you can keep it 1, and story will be, you can keep it 2, just you can keep it 3, and you can keep it same. Okay. Just click on OK. So here Here, this is the plan view. This is the plan view. Here, first thing we need to take a material M20 and Fe415. Fe415. Just go to define material properties, add new material, India concrete. Here M20 grade of steel. Just click on OK. Density will be 25 kilonewton per meter cube. Okay, add new property. Here we need to take a rebar HYSD 500. Just click on OK. Density 78.50 kilonewton per meter cube. Okay. Now we need to take a beam that is 250 by 250 by 500 using these data we have calculated earlier. Okay, 250 by 500 overall depth we are taking. Okay, so here effective depth is 50 mm. So just go to here, just go to define section property, frame section. Okay, here add new property, concrete rectangular. Here beam, just give the name like this, beam 250 cross 500. Okay, here material will be M20, depth is 500 and width is 250. Okay, here shear, we need to select the shear reinforcement material also, because we have already selected the concrete material M20, and here we need to select shear reinforcement material also, that is just select modify show rebar. Here just select the beam HYSD 415 for longitudinal bar as well as for confinement bars. Okay, here we need to put this effective depth over here, that is given 50 mm top and bottom as well. Okay, just click on OK. Again click on OK. We have already modeled the created the beam. Just take this beam command, select the beam, created beam, just select. Okay, we have selected the beam. Okay, now this beam is simply supported. Just select the joints, supports, just go to assign joints, restraints. Okay, here this is the simply supported support, just apply, click on OK. Okay, now we need to apply the load, that is service load 40 kilonewton per meter, that we have given over here. 40 kilonewton per meter we need to apply in this. First of all, I will keep it in elevation. Okay, I'll keep it in elevation. Okay, here I will make a load combination. First of I'll make a load pattern over here. Just go to define load pattern, SIDL, it is super dead. Okay, add new, just click on OK. Now just select the beam, assign frame loads, go to assign frame loads, distributed. Here we need to select SIDL and load will be how much? 40 kilonewton intensity. Okay, service load 40 kilonewton per meter. Just click on apply, click on OK. Load has been applied. Okay, now I'll make a load combination. Just go to define load combination. Here add new combo. We have two types of load combination. One is service load combination, another one is factor load combination. Here this is the service. Here one more load combination is factor load combination, 1.5 dead load plus live load. Okay, here just scale factor will be 1.5. Just click on add, select SIDL also 1.5. just click on add, live 1.5. just click on OK. We have done the load combination also. Okay, so we have done the modeling of beam. Okay, now I'll go to run analyze run this beam. Okay, just give the name like this. Just wait a few seconds. Okay, the beam has been analyzed. Analyzed. Now we need to check the bending moment, shear force and AST. Three things, and deflection also. Okay, deflection also we need to check. So first of all we need to check deflection. Okay, whether it is okay or not. Just go to display force stress diagram. Here frame pier spandrel. Okay, now keep combination, just click on apply. Right click on the beam here. This is the deflection. It is okay in deflection that we have calculated. Our structure, this beam also okay, satisfied in deflection. Okay, here also it is okay in deflection. Now we need to check what? We need to check bending moment and shear force. Moment 33, just click on apply. Just right click on the beam. Here you can see this is the maximum bending moment. Here we have calculated. Here you can see, here we have already calculated in manually. 202.14. Here also 202.14 kilonewton meter. This is the maximum bending moment. Here this is the maximum shear force 161.71. You can see over here maximum shear force 161.75 kilonewton. Similar, almost similar. Okay, so here the results are similar, manual results as well as Etabs results. So we need to find what? AST also. We need to find what? AST also. So just go to design, concrete frame design, start design check. Okay, go to design, concrete frame design, concrete frame, start design check. Okay, so this is the AST. Bottom AST we are getting 1509. Top AST we are getting 443. Here what we are getting? Here we are getting area of steel in compression zone. Area of steel in compression zone in manual we are getting 444. Okay, 444, 43.8 we are getting. Here also we are getting 443. You can see almost 99% the results are similar. Okay, here in manual we have a area of steel in tension zone 1511. In Etabs we have 1509 mm square. 1509 mm square. The results are almost similar. Okay, this is the design of simply supported beam, the doubly reinforced simply supported beam that we have seen manually as well as in Etabs. As well as in what? Etabs. Okay, this is the all about manual and Etabs comparing results of beam. Okay, thank you very much.